like to start by thanking very much the organizers for inviting me here. It's really a great honor for me to give a talk in this conference. I can see and hear from the audience and from the speakers that there are many speakers, many people in the audience who are long-time collaborators with Evgeny Kukro, and maybe know him not only mathematically but personally. In my case, I only know him from his mathematical work, both from the research work, but also, as was mentioned in the introduction, work for the mathematical community. In particular, this one result by Kukro that I've been using in several work of mine, and it will come up in my talk, which I think is nice because I don't think it has been mentioned yet today. There have been many results by Kukro, but I think I will mention one that has not been mentioned yet. Okay, so I will be talking about pseudo-finite groups, in particular infinite pseudo-finite groups. Well, for me, pseudo-finite groups infinite of small dimension, and all that will be explained what that means. But I should say that I planned this talk for like algebra seminar audience or group theorist. However, there will be some model theory notation, and in particular, I have to start by giving you two definitions from logic, which are what I mean by definable set and what I mean by elementary equivalence. So just 2 minutes on the basics of a couple of basic definitions, notations coming from logic. So I will be considering groups. I will mention once or twice fields, but essentially in this talk we only see groups. So instead of defining L structures in general, I will just define L groups. So any group G we consider as an L group structure, where this L group is the language of groups. It just contains 3 symbols, one constant symbol E and 2 function symbols. And then I consider a group as an L group structure by taking the underlying set, that has to be the elements of the group, and then interpreting these symbols in an obvious way, so that I get the group structure. And the reason why we do this is because we need to define definable sets, and for that we need to know what are formulas and what are sentences. And so an L group formula is nothing but a finite string which is built from the symbols of my language, variables, equality, logical connectives, quantors for all that there exist, and parentheses. So, for example, I've written here phi x. It's saying that for all x, xy equals yx. And of course, now there is this notion of truth. What does it mean is when I plug in A into my formula, it's clear that what I have here is that this phi A is satisfied in G if and only if A is in the center of G. Okay. And similarly, as L formulas, well, L sentence is an L formula. It should say here L group formula, which have no free variables, meaning that all variables are bound by a quantifier. For example, I have here sigma for all y for all x, xy equals yx. So the difference between sentences and formulas is that sentences give properties of groups, and formulas, they give subsets of groups. And now I can define what is a definable set. So a definable set is just the solution set of an L group formula in a group G. And so, for example, we can consider a centralizer of a given element. That's definable subgroup, or centralizer of finite many elements, or centralizer of a finite subgroup, or a normalizer of a finite subgroup, or you get definability often if you have some bounds. So, for example, if all soluble normal subgroups are of bounded soluble degree, then when you generate by them a subgroup, you get the soluble radical, which then exists, it's definable, and so on and so on. So the definable sets are just the solution sets of a L group formula. So I will be interested of definable subset or definable subgroups instead of just arbitrary ones. And two groups seen as an L-group structures, they're elementary equivalent, which is denoted by this, if they satisfy the same first order properties, meaning if they satisfy the same sentences. And so this elementary equivalence really is model theorist isomorphism in the sense that most often theorems are proved up to elementary equivalence instead of up to isomorphism. But you should note that isomorphism implies elementary equivalence. However, it's very easy to see that the other way around is not true. The easy example is cardinality reasons. So as I will say in the next slide, R plus is actually, as a group, is elementary equivalent to Q plus, but obviously they are not isomorphic. And finally, the last notation in this slide is that I denote like this a theory of a given group, which is just a set of all L group sentences which are true in this group. Okay. Now I may define pseudo-finite groups. So definition. An infinite group is pseudo-finite if every L group sentence sigma such that it's true in T, there exists a finite group such that sigma is also true in T0. Now, you note that when I say pseudo-finite, I always mean infinite. Some authors don't, but I do. And so what does this mean? It means that the pseudo-finite group is an infinite group that satisfies every sentence that is true in the theory of all finite groups. So there is this theorem called Walsh's theorem that logic students learn, which is precisely saying that first order properties go through algebra products, and hence it's an easy exercise to see that a group is pseudo-finite if and only if it's elementary equivalent to an algebra product, a non-principal algebra product of finite groups. And so here, this notation means that we take U is a non-principal algebra product, and these GIs are finite groups. And I say always for all I, so that I don't have to keep repeating that I actually mean for ultrafilter many I's. So the GIs, the I's that the GI is a finite group is big in the sense of the ultrafilter. So I may just abuse the notation and say for all I. Okay, so from now on, when I take a pseudo-finite group, you just think of group which is, well, you can think of it as an elementary equivalent to a pseudo-finite algebra product of finite groups. I listed here some examples and non-examples. I start with a non-example because if you think of the definition, it really looks like something that is easier to come up with non-examples because you just have to find one sentence that is true in your group T, but not in finite groups, or the way around. And then after I give examples. And so the first example is Z plus. And so it's not pseudo-finite because you can take sigma to be your L group sentence, which is saying that if the map sending x to 2x, x plus x is injective, then it's surjective. This is true in all finite groups, but it's false in Z plus. And similarly, you can show that, for example, proof P groups are not pseudo-finite. And in general, often if you have to show that something is not pseudo-finite, one of the strategies is to try to find a definable map so that it's not injective if it's surjective. It's not injective if and only if it's surjective. Okay. So this is the classical example of not pseudo-finite group. Then there's the classical example of or examples of pseudo-finite groups. So another thing that model theory students learn in the very beginning of the first course is that if you look at R plus and Q plus as groups, well, they are obviously torsion-free divisible infinite abelian groups. And the theory of such groups is complete, which means that every model is elementary equivalent. So that gives you these elementary equivalencies. R plus is elementary equivalent to Q plus is elementary equivalent to the third infinite divisible torsion-free group, which is here non-principal algebra product of the cyclic groups of prime order, of increasing orders. So this is a pseudo-finite group. Then the third example is perhaps a little bit more like a property. Definable subgroups and definable cosons of pseudofinite groups are pseudofinite. It's also something that is often used if you want to prove that something is pseudofinite, or if you want to prove that something is not pseudofinite. So for example, you see that the free group is not pseudofinite because if you take a centralizer of an element, it's isomeric to Z plus, which is not pseudofinite, but centralizer of an element is definable. The last example I took here is just outer product of alternating groups, where this n is bigger, ni is bigger than 5, and ni's are increasing orders. Obviously, it's pseudofinite by construction. Why I wanted to put it here is because I wanted to say that it's not simple, but it is definably simple. So I wanted to give this notion definably simple. So definably simple means no proper non-trivial definable normal subgroups. And so of course it's definably simple, because if it had the definable proper subgroup, then in the outer product, the simple groups alt n i's would have normal subgroups, which is not the case. So it is definably simple, but it's not simple. And the reason is given here. So if you consider these sequences, so elements from the Cartesian product, then when you look at so this is now the G conjugate of these elements considered as in G. They of course form a normal subgroup, and you can show that it's proper, again using Ross's theorem, by showing that elements that are fixed point free cannot be products of K-many conjugates of this form. Okay. So now I think it quite naturally anyone would ask at this point that what about simple pseudofinite groups? And so they are classified. So in my talk, I will be using this notation XF for any twist. So I usually say myself twisted Chevalier group, twisted group of Lie type over field F, possibly twisted. And so I think in here, people very well know the classification of finite simple groups. They know what I mean by a group of a Lie type or group of a twisted Lie type. But actually, usually I say when I give talks, in this talk, it doesn't even matter if you don't, because this result is something that we are not going to use in our results, because this is very much dependent on the classification of finite simple groups. Okay, so Wilson in 95 proved that if you take a simple pseudofinite group, then it is elementary equivalent to outer product of simple finite groups. That's not at all obvious, because simplicity in general is not the first order property. But he proved that. And then after, well, the only finite element is products, so you don't have to worry about products. We already the last page saw that if you take an outer product of alternating groups, you get something non-simple. And we are in the non-abelian case. So what is left is groups of Lie type, and then he proved that actually then there's a bound on the Lie rank of the group. That gives you a result that the simple group T is pseudofinite if and only if it's elementary equivalent to a possibly twisted Chevalier group over a pseudofinite field. And so this is the only time I'm mentioning pseudofinite fields. You can do the same definition as I did for the groups, but you should know that actually pseudofinite fields are algebraically classified. There's the three algebraic conditions, which is giving you if and only if a field is pseudofinite given by X. Now further, I want to mention that Rutten then in his PhD thesis generalized the elementary equivalence in Wilson's theorems to isomorphic. So even though in general we cannot do it for groups, in the simple case you can. And maybe I should also mention here that going from Chevalier group over a pseudofinite field being simple, so the direction from right to left, this uses a result of Puan. Okay, so as I said, I want to talk about kind of what can be done without the classification of finite simple groups. And so we are going to have an assumption, which is model theoretic assumption, which is true for the simple pseudofinite groups given the classification. So I'm going to give you now a definition without actually completely giving you the definition, but I'm giving enough in terms of this talk. So there is this property defined by Frank Wagner, which is the property of a theory for groups, which is called dimensionality, or in particular finite dimensionality. And so it is known that if you take a simple pseudo-finite group, then its theory is finite dimensional. And I should say that I'm using again the notation a little bit. What I wrote here is actually in Frank's terms finite dimensional, which is fine and additive, but it's okay. Here I just say finite dimensional. And so as I said, it's a property of the theory of the group. But what is enough for you to know in this talk is that if I assume group to be finite dimensional, then it means that there is this dimension function dim from the definable sets of G to natural numbers, such that anything finite is of dimension 0. There is this so-called cluster equality. So the dimension of G is equal to the dimension of this quotient plus dimension of H when H is a definable subgroup. And so in particular, it means that the dimension drops if and only if the subgroup is of infinite index. And this really is enough in this talk because we are not going to go higher than dimension 3. So we are going to be in dimension 3, and then we have to kind of deal with 1 and 2 only, because so finite is 0, and then 1 and 2, and there we are going to use this. So whenever I say finite dimensional, you just think that, okay, so we have this dimension function from the definable sets of G to natural numbers such that finite is 0 dimensional, the dimension drops when you have an infinite index subgroup. Okay. I return to the kind of introduction setup. So still we are happy to use a classification. This is a slide with lots of information in which I try to give you kind of a overall explain to you what is known overall on pseudo-finite groups. I think I managed to put together like almost everything that I know to be known of. Okay, so the soluble radical of a group, if it exists, is denoted like this. And so, of course, for a finite group, we know that the soluble radical exists. What Wilson proved that, moreover, the soluble radical is uniformly definable among the class of finite groups, meaning precisely what is written here. There is an L group formula, phi Rx, so that when you plug in a finite group G, you precisely get the soluble radical. And so what is this giving to us? It gives us the following situation. So if you have any pseudo-finite group G, you can look at the quotient G bar of G quotient by this phi R G, which is normal definable subgroup. And it's semi-simple, i.e. there are no proper non-trivial abelian normal subgroups. It's just semi-simple because that's something easily to be definable. If you think of a normal subgroup of G, not necessarily definable, then the centralizer of the conjugacy class AG, where this A belongs from here, now this is abelian normal and definable. So being semi-simple is same as being definable semi-simple. Okay, so we have this semi-simple quotient, and moreover, we know that for a pseudo-finite group, this soluble radical rho G, it exists precisely when the rho G is this phi Rg, which happens precisely when this is soluble, which happens precisely when there exists a common bound for the soluble degrees of the soluble radicals of the finite groups in the algebra product. Okay, so what this gives us is that now if you take any pseudo-finite group, you can there are two natural questions to ask. Either you can ask whether this phi Rg is soluble, or you can ask what is the structure of this semi-simple group G bar. And both of them has been studied quite a bit. Now I will mention some results. first, the result that I said that I will mention, there is this result by Kucro from 2009, which is saying that if there exists some natural number k such that the length of any chain of centralizers in your group is at most k, then this phi G is soluble of the right length bounded by k. And so he did it for finite groups, but being of centralizer dimension k for fixed k is again something you can say in a first order way. So it's true in a pseudo-finite group, and hence his result is also true for the pseudo-finite groups. And I should say that this result generalized earlier result by McPherson and Tent, which McPherson and Tent then generalized to a different setup. So here comes a couple of model theoretic definitions, which I'm not going to define. I just want to give a couple of examples of what kind of things are known. So they showed, McPherson and Tent showed that if the theory of a group is NIP, it means not independence property, then this is not soluble. And model theoretically is quite a tame property. So this example is saying that there are model theoretically quite tame properties that you can give when you still don't get soluble, when you still don't get the existence of a soluble radical. Then there's another result by Milliet, which is saying that if the theory is super simple, again, I won't define it. I will say that the example of a super simple group is a Chevalier group or a pseudo-finite field. So e.g. Pseudo-finite group with simple. Then we do know that the soluble radical exists. And what is important in this talk is that we checked with Frank Wagner, my collaborator, that if G is finite dimensional, then the soluble radical exists. And this is just by induction of the dimension. This is not very hard. Okay, but so it is studied when this soluble radical exists. And then let's look at the part about this G bar. Now, kind of, if you just think about it, how should G bar look like? It's a semi-simple pseudo-finite group. Now, if I put any assumption such that if I look at the finite groups in the ultra product of G bar, so this G bar is somehow elementary equivalent to some ultra product of GI bars, where each of the GI bars is finite and semi-simple. And if I look at the circles of those guys, so the groups generated by all minimal normal subgroups which exist by finiteness, if there is a common bound on the number of the components in these circles, so common bound not depending on I, then you would expect that in your pseudo-finite group, there is some definable subgroup which has either pseudo-finite or finite simple components, or maybe it could have some alternating groups, but they often go away if you put some tameness assumptions. Plus, and then the whole thing embeds in the automorphism groups of the products of these guys. So maybe mostly field automorphisms. So you could expect for something like products of simple groups by abelian stuff. And this often happens. So I listed here some results. I know it's a bit much, but I wanted to kind of give you a feeling that things has been studied. So the first result, theory of G is NIP. So really theory of G, and then when I go to a quotient, if I assume that the theory of G is NIP, then also the theory of G bar is NIP. This NIP is the kind of property that is not true for the pseudo-finite field. And hence in the circle, there cannot be infinite components. So the circle becomes finite, and then everything becomes finite. So in that case, G bar is finite. If you add a property which is true for the pseudo-finite fields, then exactly what I said happens. So if the theory is super simple, then this G bar is going to have a definable normal subgroup L bar, which is just a finite direct product of simple pseudo-finite groups, and this quotient is finite by abelian. Similarly, here is a group theoretic property. If the centralizer dimension of G is K, then using Kucro's result, and actually also a result of myself and my supervisor, Alexander Borovic, which is saying that in the quotient, the centralizer dimension is still bounded only in terms of K. you get that the G bar is also a bounded centralizer dimension, and you can do exactly the similar result as in this case of Milliet. And then if you want a bit more, if you want to say, for example, that one of the simple components here is definable without parameters, then you need to work more. So I just wanted to give an example. If you add more assumptions, you get more. So there's a recent result by me and my collaborator, Ukuru Kowalski, needed in a very particular situation where we added more assumptions and then got a stronger conclusion. So if we assume that the centralizer dimension is bounded, but also that all subnormal subgroups have trivial centralizers, then there is actually the so-called is just one simple pseudo-finite group, which is zero definable, meaning without parameters. And when you quotient out, you just add, well, graph automorphisms, diagonal automorphisms, and then field automorphisms. Now, I hope that this convinces you that if I take a pseudo-finite group, using the results of Wilson, both of them, we can quite well describe its structure. If you add some tameness assumptions, the tameness assumptions here, they come either from model theory or group theory, but all of these results, which are describing this semi-simple quotient, they heavily rely on the classification of finite simple groups. So they use the earlier result of Wilson. Even the one where we are saying that this G bar is finite, because the point was that there cannot be an infinite component, because if there was one, it would be a Shevalip group or a finite field or a pseudo-finite field, which kills NIP. So even when you have a result where you prove that this is finite, you actually use the classification of finite simple groups. So it is very natural to ask, what can you do without? And so I've mentioned some names here who have been explicitly asking, what can you do without? And often even more explicitly, can you classify the smallest simple Shevalip group, smallest simple pseudo-finite group without the classification of finite simple groups? So yeah, there are these papers by Elf, Chalicot, McPherson, and Rutten. Also a paper by McPherson, which is kind of a survey also on pseudo-finite groups in general. It has all of the results that I mentioned in the last page. If someone is interested, it's a very nice paper to read. Then Palashin. Okay, so several people. And so what did we prove? So now, let G be a pseudo-finite finite dimensional group. Okay, so I say that we want to study the smallest simple pseudo-finite group, smallest in terms of this finite dimensionality. Now, what would be the smallest? If you think about Shevalip groups of smallest Lie rank, so you have PSL2, what could its dimension be? Well, obviously it cannot be 1, because you can take element either, well, you can take element from the torus, and its centralizer, it's the toral subgroup. It's infinite, and it's definable, and it's of infinite index, so it cannot be 1. Similarly, you can take element from the unipotent subgroup. Its centralizer is the unipotent subgroup. And if you put them together, you get the Borel subgroup, which is now at least of dimension 2, and again of infinite index in your PSL2. So you would expect that the simple group, it has at least rank 3. And indeed, you can check that in PSL2, if the field has dimension 1, then the rank is 3. So you would expect that the smallest simple pseudo-finite group would be of dimension 3, but then you would have to know, how do the 1 and 2 dimensional groups look like? And from what I just said, you could perhaps also expect that, okay, well, maybe dimension 1 is kind of almost abelian, and maybe dimension 2 is almost solvable, and this is indeed the case. So the dimension 1 case is kind of, I wrote here folklore, because it essentially follows from the fact that if you take a pseudo-finite group, there are always going to be elements, a lot of elements with big centralizers, which is going to, what it's going to mean is that the almost center is a finite index. I haven't defined it yet, but that's how you see that this is true. And it's done, this result that dimension 1 implies finite by abelian by finite, it's done under different assumptions on pseudo-finite groups. So pseudo-finite, finite dimensional, this was done by Wagner. Then this is the paper by these 4 people. They did it for pseudo-finite, what is called measurable. Hempel, Palasin, they did it for pseudo-finite of finite SU rank. But it always essentially follows from the fact that there will be lots of elements with big centralizers and hence a big abelian subgroup. Then let us think about the pseudo-finite group of dimension 2. You should expect it to be soluble by finite because it has the soluble radical. When you quotient out, you get something semi-simple. What I just said in the last slide, if this soluble radical is not a finite index, then there will be a big infinite definable simple subgroup, which will be then the Chevalier group. So by Wilson's result and the classification of finite simple groups, there will be a simple pseudo-finite group of rank smaller than 3, which is not true. So this result of Wagner uses classification of finite simple groups. And our first result is that if G is a pseudo-finite finite dimensional group with dimension 2, then G is soluble by finite. And moreover, if it's not finite by abelian by finite, then there's a definable subgroup, which is one-dimensional. And I wrote here also Wagner himself, because Frank also proved this result like 10 years ago, but never published it without classification of finite simple groups. But the proof is like a long computation on this kind of independence property that exists there. Our proof really is the same proof that I just said, but just without the classification of finite simple groups. Namely, we directly prove that if you have a simple pseudo-finite group of rank smaller than or equal to 2, then actually the rank is 3 and it's PSL2. And that gives us the main result that I want to talk about here. So let G be a non-abelian definably simple pseudo-finite finite dimensional group. Note that definably simple really means that the components in the algebra product, the finite groups in the algebra product, they are all simple. If the dimension is 3, then G is PSL2F for pseudo-finite field F. This is exactly Wilson's. This follows exactly from the Wilson's classification. And so our result really is that this identification does not use classification of finite simple groups. Okay. And the rest of the time, I will be talking about the proof or tools of the proof first. Okay. So first, since I'm talking about results which are known using the classification of finite simple groups, I should tell you what we are using from the finite group theory. So what we use Phi-Thompson so that we get involutions, and we use Brouwer-Fowler. So up to isomorphism, there are only a finite number of finite simple groups with the given centralizer of an involution. Then the identification term that we are going to use is the following. Let G be a finite simple non-abelian and large. Largest meaning that in these results there are also some finite groups, like what I think 3 of fixed size, so bigger than those. Now, if at least one of the following holds, then we know that the G is a Chevalier group or FQ, where the Chevalier type is one of these 4. What are these one of the 2? First one is if the 2 rank is smaller than or equal to 2. So earlier we heard about rank. 2 rank is just the cardinality of the generators in the maximal elementary abelian 2 group. And so if it's smaller than or equal to 2, it just means that the maximal elementary abelian 2 subgroup is Klein 4 subgroup. So in particular, it just means that if I take these 3 distinct pairwise commuting involutions, these guys, then we have this. And so then it's proven by several people that that means that the pseudo 2 subgroups are either cyclic, generalized quaternions, or dihedral. And then, well, in the first 2 cases, there are no simple finite groups, and then there is this result by Gorenstein and Walter saying that the dihedral case gives you PSL2. And the second one is that if there exists a strongly embedded subgroup, which is saying that there exists a proper subgroup C, such that this C has involutions, and whenever we take an element in G which is outside of C, here we have, this is empty, this set of involutions, so that if you intersect C with its conjugate, oh, sorry, G should be inside here. So you intersect C with its conjugate, then there are no involutions. And so these are both things that you can say in the first order way. So what all these results that we are using here are telling us, I wrote it down, what all these results are telling us is that if you take a pseudo-finite group G, which is non-abelian and semi-simple, so the solvable radical is trivial, finite dimensional with dimensions smaller than or equal to 3, this is going to be the context that we are proving our results. Well, then first of all, Veit-Thomson tells us that there are evolutions. Brouwer-Fowler tells us that, well, since there is going to be outer product of finite simple groups, which is infinite, there will be involutions with infinite centralizer. And obviously, if I here assume that my G was simple, then every involution has an infinite centralizer. And further, if one of these two properties happens, which are here, the first order properties, then we know that our group is Chevalier group or a pseudo-finite field. So it's a dimension at least 3. And since we assume that it's at most 3, then it's of dimension 3. And the only Chevalier group of dimension 3 is PSL2. So there will be a finite index subgroup which is isomorphic to PSL2. This is all in the case where I just assume that you have non-abelian and semi-simple. But if I assume that my G, this G, is simple, then I could just conclude that it is PSL2. Okay? So this is kind of the set of tools A. And the set of tools B that I want to share quickly with you is these almost operators. So if I take a group G and a subgroups H and K, I say that H is almost contained in K if this index is finite. So the index of the intersection of H and K in H is finite. And then if H is almost contained in K and K is almost contained in H, then we say that they're commensurable, and we write like this. And so now you can define the almost normalizers and almost centralizers and almost centers just up to commensurability. So they are here. They are nothing surprising. Just centralizers and normalizers up to commensurability. And you would, of course, want to ask kind of, is it uniform? So uniform just means that commensurability is uniform in the almost normalizer of H in K if there is some M such that whenever H and its conjugate are commensurate, then actually this index is smaller than N. And similar for the almost centralizer. And if your group is finite dimensional, then it's well known, and it's not very hard to see that if you take definable subgroups, then commensurability is uniform in these operators, meaning that these subgroups, they are going to be definable. If you take a definable subgroup, then it's almost normalizer, almost centralizer is definable. And so there is this result by Schlichting, which is much more general than what I've said here, and a definable version of it by Wagner, which is in the same level of generality as the result of Schlichting. But all we are going to need in this talk is that it's known that if you take any group and a definable subgroup, if G almost normalizes H, then G has a normal subgroup, which is commensurable with H. So what is this giving us is that if I now take a pseudo-finite finite dimensional group, again of dimensions smaller than or equal to 3, which is where we're working, and then you take a definable subgroup with dimension 2, such that it's not almost normalized by G, then I know how the almost centers look like. So the almost center of H is either finite, or this almost center of G is infinite. And again, what does it mean in particular for the simple case? If G is simple, then its almost center is trivial. So it's saying that every rank 2 subgroup has a trivial center in the simple case. Okay. Now I'm starting to be out of time, so I will show you the key lemma. Let me first recall that if you take a PSL2 or a pseudo-finite field, it's finite dimensional of dimension 3. And one of the properties that it has, which is not true in any other simple pseudo-finite group, is that every centralizer of an element, non-trivial element, is of dimension 1. And so the key lemma that we use in both of the theorems that I said in the beginning is the following. If G is a non-abelian and almost simple, I've defined almost simple here, not abelian by finite and no definable normal subgroups of smaller dimension. So non-abelian, almost simple, pseudo-finite finite dimensional group of dimensions smaller than or equal to 3, you assume that the centralizers of involutions are as in the simple case. And you assume that one of the following happens. Either this property that is true only for the PSL2 among simple pseudo-finite groups, or the second one is saying involutions behave as in a PSL2 over a pseudo-finite field when the field is not of characteristic 2. This is what this one is saying. If you have a rank 2 subgroup, you think of it as a Borel subgroup. I take two distinct involutions. If the characteristic of the field is not 2, then they have different centralizers. So in particular, the almost centralizers of the centralizers of involutions are different. So if one of these happens, then we have that this dimension of G is again 3, and G has a finite index subgroup, which is PSL2 over a pseudo-finite field. And I was never planning on giving you the proof. I was like in one line, the proof idea. We have involutions by Veit-Thompson. By the assumption we have that the almost centralizer of the centralizer of involution is commensurable with the centralizer of involution. If this definable subgroup is strongly embedded, we are done by the tools A. For otherwise, we find involution from here, just by the definition. And then using our setup, we prove that the M2 rank is smaller than or equal to 2, and then the claim follows. And I'm going to say, remark, theorem 1.6 easily follows from this, simply because, as I said, now this means that simple dimension 2 pseudo-finite group cannot exist, because such group would satisfy this condition. It cannot have centralizers of the same dimension as it is. So the first term really follows. And the main theorem, since I'm out of time, I won't be going through the proof. I'll just say that the main theorem, you assume that 1 doesn't happen, you study the rank 2 subgroups, and you prove that the 2 happens. And then you apply the key lemma. But yes, I am out of time, so I will not go through the proof of the main theorem. I will stop here. Thank you.